So thanks, Giuliana, for the introduction. This is a joint work with Paola Bonizzoni and Paweł Gawrychowski. And as you can see from the title, the topic is measures of distance for fully labeled trees. So let me start by giving a good reason for studying such objects. As you may know, a phylogenetic tree represents the evolutionary history of a group of species. So the leaves of a classical phylogenetic tree are labeled, each label being one of the species, while the internal nodes represent extinct ancestors and are therefore unlabeled. The situation is different when one wants to study the evolutionary history of the mutations of the cells of a tumor, because what generally happens is that ancestors are alive at the very same time as their descendants here. So this translates into the model into internal labeled nodes. So tumor phylogenetic trees have each node labeled with a distinct label representing a mutation, and this is what we mean by a fully labeled tree. So, of course, defining and studying measures of distances for such objects is important, for example, to evaluate and compare the output of different inference tools for inferring tumor phylogenies. Anyway, this work does not pretend to provide a practical method for comparing tumor phylogenies, and instead it focuses on the theoretical aspects of the problem. So what we have in input is a pair of rooted trees fully labeled by a finite set of labels, and we are going to consider two operations on such trees, namely link and cut and permutation. These operations and distances were introduced by myself and my colleagues last year in CPM. So a link and cut operation simply consists in cutting one edge of one tree and linking the pending subtree we obtain to another node of the tree. So in this case, we effectively switch the parent of the black heart from the blue flower to the green spike, for example. And the permutation operation consists in renaming the labels of the tree according to a given permutation. So, for example, here the pink spike will become a red square and so on. So we obtain an isomorphic tree that have different labeling of its node. One can define two distinct distances based on such operations. The first one, the permutation distance, is only defined between isomorphic trees, and it is the smallest size of a permutation that transforms one tree into the other, the size of a permutation being the number of elements affected by the permutation. And the rearrangement distance is defined between any two trees, not necessarily isomorphic, that have identical roots. And it is the smallest size of any sequence of link and cut and permutation operations that transforms one tree into the other without permuting the root. Of course, one could also define a distance based on link and cut operations only, but we already studied this distance last year. It turns out that it is linearly computable and there is no mystery there. So we won't consider it again in this paper. So the result. Last year, we were able to prove that the permutation distance is polynomially computable. We provided a very simple cubic algorithm. And while the rearrangement distance, it is MP hard to compute. And we provided a constant factor approximation algorithm for the spatial case where at least one of the two trees is binary. In this work, we reconsidered both distance. For permutation distance, we were able to prove that it is equivalent to bipartite maximum matching up to polylogarithmic factors. And by plugging in the currently fastest known algorithm for bipartite maximum matching into one side of the reduction, we obtain an order of n to the 4/3 plus something small polylog time algorithm for permutation distance. As for the rearrangement distance, we design a constant factor approximation algorithm that works for any two trees without any restrictions on the degree of the trees. So I won't present the result on the permutation distance here due to the lack of time. One side of the reduction is rather easy, so reducing bipartite maximum matching to permutation distance is not too difficult. But for the other side, we need more refined tools such as heavy light decomposition and the result by Cow and other that states that one can reduce an instance of bipartite weight matching to multiple instances of bipartite maximum matching in time linear to the total weight of all the edges of the original weighted graph. So today I will only mention the result for the rearrangement distance that is more audience friendly and easier to present. So to be precise, for ease of presentation, we are not considering the original version of the rearrangement distance, and instead we consider an extended version that works for fully labeled forests instead of trees. And it is defined based on the following equivalence relation between fully labeled forests. So for each label, either it has the same parent in both forests, or it is a root in at least one of the two forests. So two forests are equivalent if and only if one of these things happen. So we can define the rearrangement distance between two fully labeled forests as the smallest size of any sequence of cut and permutation operations instead of link and cut and permutation operations that transforms one forest into another forest which is equivalent to the target one without permuting the root. So this requirement on the root is only a technicality that allows us to prove that when this notion of distance is applied to trees instead of forest, it is in fact equivalent to the original notion of rearrangement distance. Before describing you the approximation algorithm, let me point out which are the difficult situations, the things that make the problem hard. For example, consider labels 11, 12, and 13 here. As you can see, they are children of label 7 in the first forest, but they are going to be children of 3 in the second one. So one may think of permuting labels 7 and 3 so that by performing a permutation of length 2, so of course 2, we fix the situation for 3 labels. So it seems convenient. But as you can see, if one performs such a permutation, it is possible to spoil the relationship between the labels we permuted with their own parents. Because at the beginning, 7 was a child of 2 in both forests, or 3 in this case. But now this relationship is spoiled. So one thing is that is not easy to balance between benefits and drawbacks of any permutation operation because of this issue. And not only that, it is not always clear which label would be convenient to permute with which other. For example, focus on labels 4 and 5 here. They are children of 2 in the first forest, but they are going to be children of 3 in the second one. So even if I knew that permuting something would be beneficial here, should I permute 2 with 3 to fix the situation for 2 labels without affecting their parents in this case, or should I permute 7 with 3? So this is another W situation that is not easy to resolve and makes the problem hard. Okay, so now our algorithm consists of 4 steps. Each step will add more and more structure to the problem in order to resolve the dubious situations I just presented you. And for each of these steps, we will be able to guarantee that the number of operations we perform will be within a constant factor from the shortest possible sequence of operations. So in the figure, we will guarantee that arg I will be order of the distance between the forest obtained at the previous step and the target forest. And then, by repeatedly applying a triangle inequality, we can guarantee that the whole algorithm is in fact a constant factor approximation algorithm. Okay, so the first step consists in resolve the first W situation I presented, namely to avoid that by permuting some labels, we affect the relationship with their own parents. What we do is for every misplaced child, such as 12 here, instead of cutting the edge that links that child to its parents, we cut the edge that links its father to its grandfather. And this is because if we wanted to permute the parents to fix the children, we don't have to worry about the relationship with the grandparents. So in this case, we only have to cut 3 edges. We obtain this forest F11, and I won't show you how, but we are able to guarantee that we only lose a factor of 4 here with respect to the actual distance. The second step is the first step in resolving the second W situation, which is who it may be possibly convenient to permute with whom. And what we do is for each node of F11, we let their children vote for their representative in F2, where a representative is their parent to be. For example, 11, 12, and 13 are going to be children of 3 in F2, so they all vote for 3, while label 14 is going to be a child of 2, so it votes for 2, and so on and so forth. And then for each node of F11, we look at the representative their children have voted for, and we cut all of the edges of the children that voted differently from the majority. For example, for 7, 3 out of 5 children voted for the same node 3, so we cut the other 2 nodes. At the end of this step, the property we have is that no 2 children of a node in the forest we obtain have different parents in the target forest. So the survival children are not split in the target forest. So we obtain this forest here, and we are able to prove that we only lose a factor of 2 in this step. Now, it still may be the case that even if the children of each node in F12 voted for the same representative, it can still be the case that 2 different nodes have children that voted for the same representative in F2. And we want to get rid of this situation so that we can define unambiguously a permutation at the end. So what we do is kind of the symmetrical of step 2, and it is consider all of the nodes in F12 that whose children voted for the same representative, only keep the one that have more children and cut the rest without any mercy. So at the end of this step, not only every node in F13 will have children that voted for the same representative, but no two different nodes in F1.3 will have children that voted for the same representative. And again, we lose a factor of 2 also because it was kind of the symmetrical of the previous step. And we have a final step where we perform the only permutation that makes sense now, which is we permute every label with the representative of its children. So in this case, 8 and 9 are already well placed. So we permute 7 and 3, and we obtain a forest which is equivalent to the target one according to the definition I gave before. And we lose at most a factor of 4 during this step. And this is the whole algorithm. So there are a couple of open questions. First of all, since we lose a factor of 2 or 4 at every step, the constant factor of the approximation algorithm is not really small. So one can ask themselves if it's possible to lower the constant factor of this algorithm, and probably it is with some care. And another thing one can ask is whether there is any approximation scheme for the rearrangement distance. That's it. Thanks for your attention.